Welcome, crew. This is a continuation of our optimization notes where we write an equation for a quantity, right, that needs to be maximized or minimized, which leads to a quadratic equation. So that quadratic equation would have a graph that would be a parabola, so either a happy parabola or a sad parabola, right, where because they turn around have an absolute minimum at the vertex or an absolute maximum at the vertex. And we know how to find the vertex of a quadratic. We have a formula for finding the x-coordinate, the value of the independent variable, right, which we call h for the vertex, and that is negative b over 2a. And to find the y-coordinate, which we call k, we simply plug the value of h into our quadratic equation, and that gives you our value of our dependent variable, or our y. Okay. And then we use that to answer the question. What we're going to look at today are economic optimization problems, which are going to use a basic relationship that we're already familiar with. So, and that relationship is that rate times time equals distance. If we follow the units of that, let's say our rate is how fast we're traveling, measured in miles per hour, and our time is measured in hours. If we multiply those together and do unit analysis, the hours would divide out, and what we would be left with is miles, which is a distance measurement. The relationship we're going to use here is the one that says our cost per item, say, times the number of items will give you the total cost for all items. So if, for example, we had a cost per item in, so I don't know, let's say in dollars per boxes. So our items are, we're buying boxes, so dollars per box, and we multiply that by a number of boxes, right? Unit analysis would divide out those boxes, and what we would be left with is dollars. So another example might be that if we had dollars per day, so let's say we're working and we earn so much per day, and we multiply that by the number of days we work, again, the days would divide out and we would get dollars. So these are optimization problems where we're multiplying two quantities together and the result is a certain amount of money. So here's an example we're going to look at. We've already looked at example 1 and 2. If we go back here, we're going to look at this trucking problem. So this says a trucking company has determined that the cost per hour to operate a single truck is given by C of S equals 0.001 S squared minus 0.01 S plus 12. So this cost per hour is given the variable capital C, and lowercase s is the speed that the truck travels. So those are our two variables. And the question is, at what speed? So this is asking us to find the speed. So find S, right, is the total cost per hour, right? So find S when the total cost per hour, capital C, is a minimum. Okay, so we're going to walk through that process using our graphic organizer. So I'm going to come down here and I'm going to pull out this graphic organizer. So here's what we have. Not really a picture to draw here. We are minimizing, right, the cost, and we are finding the speed. Right? So we're minimizing cost, capital C, and we're finding speed, lowercase s. S is the speed of the truck. Capital C is the cost per hour. to operate the truck. We're given an equation that's kind of nice. So our equation is that C of S is 0.0001 times S squared minus 0.01 times S plus 12. Right? So that is already an equation in one variable, which means that we don't need a secondary or constraining equation. Right? The domain for that variable, right, S is the speed of the truck. So if we think about it, right, in order for the truck to travel anywhere, its speed has to be greater than 0, and I'm sure there is an upper limit to that speed, but without knowing it, let's just go to infinity. That would be one fast truck. So now let's find and interpret our, before we do that, let's go back and look at this. So this is our equation, right? This is a quadratic equation, right? It is a happy quadratic, so its graph is going to be the graph of a parabola, right? And it will have a minimum at the vertex. So the vertex, which we call HK, is going to give us a minimum cost for a specific speed. So here we go. We can find the vertex. We have a formula for that. In this case, that would be the opposite of our B, which is negative 0.01, divided by 2 times our A, which is 0.0001. Right? We simplify that and we get 50. Well, what is 50? 50 is the speed of the truck. Right? It's our independent variable, and it is measured in miles per hour. Okay? So do we need to find K? Well, K is our Y variable. Our Y variable is a value for the cost. And yes, we need to know what that cost is, and that's a cost per hour in this case. So to find that, we're going to come in here and we're going to find C of 50. So we've got 0.0001 times our speed, 50 squared, minus 0.001 times 50 again, plus 12. We simplify that and we get 11.75. That is a cost per hour, so that's in dollars, right, per hour. So this is our cost for operating the truck per hour if we travel 50 miles per hour. So in a sentence, our solution is that the truck needs to travel at 50 miles per hour to minimize the cost per hour of operating the truck. Good. So we've used math, used quadratic equations, and the vertex to answer a question that would be pertinent to someone who runs a trucking company. Let's look at another example. So we're going to come back and we're going to look at this example 3. So this tells us that a real estate company owns 100 apartments at $1,000 per month, right? This is the rent for one apartment, right? So that's the rent per apartment. Each apartment can be rented. However, for each $50 increase, there will be 2 additional vacancies. How much did the real estate company charge for rent to maximize its revenues? So we've got a table here that's just helping us to look for the relationship between the rent and the apartments rented. Well, let's call the rent R. That could vary because we can increase the rent, right, by $50. And let's call the number of apartments rented A. So A is the number of apartments we rent. So this $50 increases is our number, right, of $50 increases. So if we don't raise the rent at all, so we have 0 increases, then our rent is going to be $1,000 per month. right? And at that rate, it tells us that that each apartment can be rented. And there are 100 apartments, so 100 apartments would be rented. What's our revenue? Let's call that revenue capital R. Revenue is the amount of money that comes in, and so that revenue is going to be our 1,000, right, dollars per apartment times our 100, which is $100,000. So that's our revenue if we don't change the rent at all. Now, if we increase the rent one time by $50, then our rent is now $1,050. Right? But what this tells us is that every time we raise this rent, there will be 2 additional vacancies. So instead of renting 100 apartments, we would rent 98. And our rent then would be what 1,050 is times 98. If we multiply that, we have a revenue of $102,900. So you can see that even though they don't rent 2 apartments, their total revenue increases, right? So that would be a good thing to this rental company. Now, if we raise the rent twice, so 2 is the number of $50 increases, then our rent is now, what, $1,100. So 1,000 plus 50 plus another 50. And the number of apartments we rent goes down to 96. So our revenue is 1,100 times 96, which is $105,600. So again, better yet, if we do 3 increases, our rent is now 1,000 plus 150. The number of apartments we rent drops by another 2, so becomes 94. And we multiply 1,150 times 94, and our revenue is now $108,100. If we do 4 rent increases, so 450s are 200, so our rent is now 1,200. The number of apartments drops down to 92, and if we do 1,200 times 92, we get $110,400, right? Every time we raise the rent, we rent fewer apartments, but our revenue is going up, right? So it sounds like the more rent increases, the better. Well, what if we raise this rent 50 times? Well, 50 times 50 is 2,500. Added to our 1,000 makes the rent per apartment $3,500. Well, what would happen to the number of apartments we rent? We started at 100. We lose 2 every time we raise the rent. So 2 times 50 is 100, which means the number of apartments I now rent is 0. I can't rent any apartments. And my revenue is going to be 3,500 times 0, which of course is 0. What happened to my revenue? Right? My revenue was increasing, but now it's dropped to 0. So somewhere there must be a point where there's a maximum. Well, in order to find where that is, let's let X equal the number of $50 rent increases. So X is not the rent. X is not by how much we raise the rent. X is the number of times we raise the rent by $50. So my rent, right, becomes what it started at, which was $1,000, plus $50 every time I raise the rent. So 1,000 plus 50x. What about my number of apartments? Well, it was 100, but every time I raise the rent, it drops, so we subtract by 2 apartments. So that's 100 minus 2x. And my revenue then is going to be my rent 1,000 plus 50x times 100 minus 2x. And that would be an equation for my revenue in terms of x. Right? And you can see that if I were to multiply these 2 together, multiplying the 50x and the negative 2x together would give me negative 100x squared. And I'm going to have a quadratic function, right? And we're going to do this problem again using our graphics organizer. So I'm going to come down here, and we're going to use our graphics organizer. So again, no picture to draw, right? But we do have a situation where we are trying to maximize revenue. And what we are to find is the rent per apartment. So in our variables, let's let R equal that rent per apartment. Let's let A equal the number of apartments rented. Let's let X equal, right, the number of $50 rent increases. And we're going to let capital R equal the total revenue, the total amount of money that comes into this realty company. So my equation to be maximized here is going to be equation for the revenue, which is the rent per apartment times the number of apartments, R times A. That is in two variables, but I know something else. I know that my rent per apartment, right, starts at $1,000 and will go up by $50 every time I raise the rent, so 50 times X. I know that the number of apartments I rent starts at 100 and will go down by 2 every time I raise the rent, so 100 minus 2X. So if I replace R and A with these quantities, I get an equation for R, right, which is 1,000 plus 50X times 100 minus 2X. And that is an equation for revenue in terms of X. What's our domain for that variable, so for X? Well, we could not raise the rent at all, which makes X 0, or we could raise the rent we saw up to 50 times, right, which would take our number of apartments rented down to 0, right? So that would be our domain in this case. For me to find the vertex, I'm going to need to multiply this together. So if I multiply this, I FOIL this, I get 100,000, right? That's for my first. And then my outers would be negative 2,000, my inners positive 5,000. So that would be plus 3,000 X minus, right, the 50 times the negative 2X would be 100 X squared. That is a negative quadratic where the maximum will occur at the vertex. So if I want to find H will equal the opposite of my B, so that's negative 3,000 divided by 2 times A, so 2 times 100,000. I divide that out and I get 15. And 15 is a value for my independent variable, which is X. So 15 is the number of $50 rent increases. Again, we are not raising the rent by $15. We're raising the rent by $50 15 times. My revenue, right, so this is X. K is going to be my revenue. My revenue will equal, right, what R of 15 is, which is going to be 1,000 plus 50 times 15 times 100 minus 2 times 15. Well, 50 times 15 is 750, so that makes this 1,750. 100 minus 2 times 15, 100 minus 30 is 70. And I multiply that together, and I get $122,500. Right? So I needed to find the amount to charge for rent, so I didn't really need this, right? But my amount to charge for rent, right, is this R, which is my 1,000 plus 50 times 15, which is 1,750. Right? So the answer to the question is, right, the real estate companies revenue will be a maximum if they charge $17.50 in rent per apartment. Right. That's all we had to answer. We actually found more information than that, right? Just in case we had a question that asked us to go farther. This number, this 70, is the number of apartments that they would actually rent. So they would have 30 apartments left vacant. And as we said before, right, this value is the total revenue that they would bring in per month. So there we go. You're going to do a couple problems like that. You've seen how to use the table to help you come up with a relationship and an equation, and then we also did that through the graphics organizer. So you're going to do a problem tonight, and then we'll do a couple in class tomorrow.